All right. Hey, everyone. I'm Nilanshu. I'm a software engineer at Apple, where I'm part of the Valkey team. Over the past few months, I have been working with the community to build Valkey-Swift, which is a new Swift client for Valkey. And today, I'm excited to talk about some of the lessons that we have learned around doing some of the good things for Valkey-Swift. Before we start, just a quick introduction to Valkey-Swift. It is the first native production-grade client library written in Swift. It is open source, and we did the first major release 1.0 early this year. It is also a Valkey community-endorsed Swift client, so you'll find it listed under the client section on the official Valkey website. All right, now that we all are a little bit familiar with Valkey-Swift, does this look familiar? So here it goes. So your tests pass, and you deploy to production on Monday. On Tuesday, you check your production is fine. But on Wednesday, an event happens. A Valkey node fails, or the DBA comes in and reshards the data from one node to another. And now you see request failures, high latencies, errors which won't recover. So this is exactly what happens when the client doesn't handle all those unexpected scenarios that can happen on the server. So what does a production-grade client do? So you as a developer want to focus on your business logic. You expect reliable responses and predictable performance from your dependencies such as Valkey. But the reality on the Valkey cluster is different. There is all sort of scenarios like reshardings, failovers, and network partitions that can happen. So the role of the production-grade client, among other things, is to handle those unexpected scenarios and act as a bridge layer between the user service and Valkey cluster, which is reliable, resilient, and efficient. So now that we all have some background, let's get into the lessons from Valkey-Swift. Just a quick disclaimer, these lessons are not specific to Swift. These are language agnostic, and you can apply them to client implementations in other languages as well. The first series of lessons are around enhancing resilience. So one core philosophy that we have followed in Valkey-Swift is to minimize impact to both client and server under unexpected scenarios. Let's take a look at an example of this through graceful degradation. So when a Valkey node restarts, every client that is connected to it is going to notice that this node is down around the same time. If they are all configured to retry after the same fixed interval, they are going to do the next retry together, very close to each other. This is going to overwhelm the server. The server will start to drop connections, which is going to cause more failures, more retries, which are again together, very close to each other. And this loop is famously called as the thundering herd problem. Previous speakers have alluded to it. So let's see how we solve this problem in Valkey-Swift. So in Valkey-Swift, when the connections start to fail in the connection pool, the pool moves to a degraded state. In this degraded state, we exercise caution. So we don't run the new incoming requests. We start queuing them. And from this queue, we pick just one connection, and we just retry that. And we retry that connection with jitter and back off. The jitter introduces randomness in request timings and spreads them apart. So this kind of creates a back pressure, and it gives server ample chances to recover in case of transient failures. If the connections are still failing, then we know we are in a bad state. So we move to a failed state where we open the circuit, the request failed fast. All this while we are probing in the background, and when those probes succeed, we move back to the running state and restore everything up. So this way, we degrade gracefully when things start to go wrong, and we give ample opportunities to server to recover in case of temporary failures. The next lesson is to handle failures optimistically. So the traditional approach that I've seen in some clients is pessimistic, which assumes for the worst. So it takes proactive measures to handle errors. The Valkey-Swift approach is optimistic, which assumes for the best. So we take reactive measures to handle errors. Let's see this via an example. When a Valkey client sends a command to the wrong node, Valkey responds back with a moved redirection along with the target node. So the traditional approach is pessimistic. We stop the request, we refresh all slots synchronously, and then we retry the request on the target node. But this is problematic because we block the request for the entire duration of the refresh, which could be slow. But Valkey-Swift takes a different approach. When Valkey-Swift gets a move redirection, we first of all update that fact in our slot map, and then we ask this question: do we know this node? If we already this node, then this is just a scenario where we resharded the data from one node of the cluster to another node of the cluster. So we skip the refresh entirely. We just retry the request on the target node, and we are done. Pretty fast. If we don't know the node, then this is a scenario where the cluster was expanded. So what we do is we first create a connection pool on the fly to the target node. We retry the request, and we finish the request on the target node, and then we do the refresh later async. So either way, both yes and no, we first focus on finishing the request and then do the heavy lifting of refresh later, only if needed. With pessimistic approach, a simple resharding can easily take more than tens of milliseconds, but with an optimistic approach, we can finish that simple resharding within a millisecond or two. The next series of lessons are to enhance reliability by minimizing bugs. We'll see multiple ways where we have tried to eliminate bugs in Valkey-Swift. So Valkey has over 400 commands. Writing all those commands by hand is going to be tedious, and we know that when humans do manual tedious stuff, they tend to make more mistakes. So we built a code generator, which consumes the command JSON specs, and it generates the command code, the Swift code for those commands. The command JSON spec already contains info like the command arguments and the response types, and it generates Swift code like the Swift struct to represent those commands, and methods, convenience methods to execute those commands. Code generation is really a two-step process. In step one, we clone a particular version of Valkey server. This already has the JSON specs. So we merge these JSON specs into multiple files, and we give these files to step two, which consumes those JSON specs. It parses them, and it maps the data type in the JSONs to the Swift types, and we generate Swift code. We generate about 20,000 lines of Swift code for commands this way. Code generation is also fast, reliable, and future-proof because in future, when Valkey adds new commands, we can just invoke this code generation once, and we get all those command implementations for free. Yet another category of bugs that exist in client implementations are orphan tasks, which keep running in the background when you don't need them, and connections which just silently leak. Traditionally, eliminating these bugs have relied on developer discipline, where you as a developer manually track all your tasks and you clean them up when you don't need them, and you ensure to release that connection back to the pool when you don't need it. But this is error prone, because you might as well miss canceling that task which you don't need and it suddenly becomes an orphan, or you miss releasing that connection back to the pool and that becomes a connection leak. So we have solved this problem using a Swift feature called as structured concurrency. This feature naturally brings structure to your code. It establishes a parent-child relationship between the tasks. It ensures that the child tasks cannot outlive the parent task, and when you cancel the parent task, all of its children automatically get canceled. So this way, when the parent client task gets a cancellation call, that cancellation call trickles down the entire task tree, and it kills all the child tasks, such as the pools, the timers, and the refresh tasks. We didn't write any cleanup logic for this. We just composed our tasks using Swift structured concurrency principles, primitives, and we just let Swift structured concurrency take care of the cleanup. Now, combining Swift structured concurrency for task lifecycle management with scoped closures for resource lifecycle management ensures that the leased out connections are always released back to the pool under all scenarios. Success, failures, cancellation. Now, Swift structured concurrency or structured concurrency isn't just something that is specific to Swift. There is other languages like Kotlin that already supports it, and more popular languages like Java, Python, and C++ are catching up to support it in future versions. Yet another category of bugs are data races. This is a scenario where multiple tasks update the same shared mutable state at the same time, concurrently causing inconsistent results. And traditionally, data races cannot be identified at compile time. They only show up at runtime in your production. And just like orphan tasks and connection leaks, data races also rely, or prevention of data races also rely on developer discipline, where you manually protect your shared mutable state via locks and those synchronized blocks. But this is again error prone. You miss locking it, and you run into the data race. So with Swift 6 strict concurrency mode, the compiler has automatically started to enforce data race safety. The shared mutable state is now a part of an isolation domain, and all the tasks that wish to update that mutable state go through that isolation domain only one task at a time. The compiler guarantees it. The compiler also checks that the data that is crossing these isolation boxes boundaries is safe to share. For example, it is going to allow you to pass immutable classes, but it is going to prevent you to pass mutable classes. If you try to do that, the compiler is not going to allow you that. Your compilation will fail. And if you have a data race, you have found it on your desk, not in production. Now, compile time data race safety is a rare feature in languages besides Swift. Rust also supports it, but I hope more languages in future do that. And the last series of lessons is to enhance efficiency, because it is crucial for a client to run with a lean resource footprint. So every allocation that we do of the heap doesn't just cost us the bytes that we reserve. It also burns CPU cycles to allocate the memory, to free the memory, and then to move the bytes from one location to another. So we have tried to minimize the allocations that we do in Valkey-Swift. Let's see one example. In some clients, when the Valkey response bytes first arrive in a socket read buffer, those bytes immediately get copied to an intermediate buffer so that the socket read buffer can be used for the next read from the socket. Then this intermediate buffer is then converted into the typed responses which the user needs. But this intermediate buffer is just a temporary throwaway space to store those bytes temporarily. Valkey-Swift avoids this entirely by ensuring that the user responses are just directly pointing to the neo byte buffer, which is the buffer where the responses first arrived. The user just consumes those raw bytes directly, and they convert them to the types that they want when they want. The benefits of this kind of zero copy parsing compound in case of big responses, such as those lists with 100 or thousands of items. In that scenario, we didn't allocate anything extra, and we saved ourselves memory and CPU. So to recap, we looked at techniques like graceful degradation and optimistic failure handling to minimize impact. We saw code generation for Valkey commands and their benefits. We also saw how we prevented issues like data races, connection leaks, by using language features instead of relying on developer due diligence. And we saw how we run with a lean resource footprint by avoiding unnecessary allocations. This brings us to the end. We are looking for contributions to Valkey-Swift. So feel free to check it out. And I'm available after the talk if you want to catch up. Thank you.